I was invited recently to be in Google's beta test group for its new AI engine, which they call Bard. Knowing this episode of the podcast was all about quantum physics and quantum mechanics, and knowing very little about that subject myself, I decided to put Bard to the test. I requested Bard tell me a joke where the object of the joke is how people do not understand the concept of quantum physics. Here was Bard's response. What do you call a physicist who explains quantum physics to a layman? A miracle worker.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Hello and welcome to the Reliability Matters podcast. I'm your host, Mike Conrad, and I'll be your guide to all things reliability within the electronics industry. For those of you who are counting, this is episode number 119. On this podcast, we discuss the latest trends and technologies in circuit assembly reliability, as well as providing tips and advice on how to improve the reliability of your products. We talk to industry experts, engineers, and researchers from all over the world, sharing their insights and expertise on how to design and assemble reliable circuit assemblies. If you're interested in learning more about the reliability of circuit assemblies, then this is the podcast for you. So subscribe now while you're thinking about it. Hit subscribe and join us on this journey for reliability. So by now, we're all aware of the term quantum physics and quantum mechanics. But if you're anything like me, you may have little understanding of what those terms actually mean. I first met my guest at the SMTA Pan-Pacific Symposium in Hawaii just this past January. He was presenting a paper entitled Quantum Technology, a Theoretical Overview of the Possibilities. The more I listened to and watched his presentation, the more I wanted to learn about quantum physics and mechanics. So I selfishly invited him onto my show today so I could learn more, and perhaps you can too. My guest today is Dr. James Whitfield. Dr. Whitfield is an associate professor of physics at Dartmouth College. He earned his Bachelor's of Science in Chemistry and Mathematics from Morehouse University and his PhD in Chemical Physics from Harvard University. He was a postdoctoral fellow at Columbia University in New York, Vienna Center for Quantum Science and Technology in Vienna, and Ghent University in Belgium. And he is currently an Amazon visiting academic. And even better than all that, he's my guest today on the Reliability Matters podcast. So, without any further ado, it's my pleasure to welcome Dr. James Whitfield to the show. Well,
hello.
You survived the joke.
That's pretty good. I mean,
was Bard accurate? Sometimes do you feel a bit like a miracle worker?
I mean, I do my best to try to explain things as I understand them, but I've been trying to put together explanations since I got started. I guess explaining stuff to myself and then to other people. But yeah, I don't know about miracle worker. I mean, you do your best, right? Hope that teaching goes well.
Right. Well, I think in your world, though, unlike when you're speaking at a conference like you did in Hawaii in January, that audience didn't necessarily show up to learn quantum mechanics, to learn about quantum mechanics. They showed up to learn about a lot of things, which I think makes it more challenging for the speaker, because you have to speak to people who are interested in hearing what you're saying and people who you're part of the program, right? You're just part of the program. But in your academic world, all of your students signed up for your class. So one would assume there's some, inherent level of interest in the subject, or they're masochists or whatever. They knew what they were getting into. So, and I assume they want to learn more. What drew you to the whole topic and the whole science of quantum technology? One doesn't just wake up out of bed one morning at 9 years old and go, I want to be a quantum mechanics physicist, or maybe that does happen. Tell me about your journey and how you got to where you are.
Maybe wake up in your bed, maybe not at 9, but at 19, you're just like,
Okay.
what should I do? my life. You already been doing math and science. And then I think one of the most interesting aspects of my career, I think one of the major points was first time I went to grad school and I got a check, my graduate student stipend, and I was just I was so happy. I was so happy. Not even the amount, I don't remember how much it was. And it wasn't much, but I think I was just very happy that someone's paying me to study. Like, it's just like, this is one of the best things in the world. I'm just supposed to learn things, and I like learning things. I like going deeply into things. And so, having an opportunity to keep learning and learning and learning, and then going from one side of the classroom to the other side of the classroom, is really how I got there. I think for me, it started much younger. You talk about being 9. I really like math and science because it's a very quiet space to work. People talk about meditation and praying and things like this. For me, this is as close as it gets, or, maybe even the same thing, because you're sitting there and I have my mom's old books. So like her old books from college, and I go back and do intervals, just to calm down. I'm really emotionally upset, or someone's said something to me I didn't like, and I just do an interval. If you don't get it, do the next one. If you don't get that one, do another one, right? Just, very quiet space. 4+4 has no emotion in it. I mean, maybe it has some emotion to you, but that's personal emotion, not about what someone said to you last week or whatever. So I really enjoyed that aspect of math. I started off pre-med, and then I didn't want to be a doctor, so I just had a chemistry degree, and then a math and a chemistry degree, and then I went off to grad school and started doing quantum computing. My advisor had just written a paper about quantum computing right before I showed up, and that was the project they put me on, and I've been doing quantum computing, quantum chemistry pretty much ever since. I mean, a mix of a lot more things, and I really enjoy quantum theory, quantum mechanics. There's so many things to bring in, from computer science to engineering to math and to chemistry and physics. Goes all around, and I really like the ability to kind of look in many different places and still have one grounding topic to stay at.
Yeah, I think I'm no mathematician, but one thing I really enjoy or even respect about math is it's truth. Math is truth. Unlike maybe some liberal studies, English and art and things like that are very subjective. There's a person's truth, which may not be the other person's truth. But in the world of mathematics, it's a universal truth, right? Because 2 + 2 is 4 to me, and 2 + 2 is 4 to you. And, unless someone, is a little bit nuts and just doesn't agree with that, and can show, can back it up scientifically, it is a universal truth. It never disappoints. And sometimes it's hard to get to that truth, but once we do, we realize that it was there the whole time. We're just discovering it. And speaking of discovery, this whole quantum field, a topic today seems to be, at least from a layman's standpoint, from my standpoint, it seems to be relatively new. I don't think we were studying quantum physics in the 30s, for example, or maybe we didn't know we were, or we had another term for it, or maybe it was a foundation. But but it's not like we're discovering something that didn't exist. We're discovering an understanding of something that has existed since the beginning of time. So how much is in quantum physics and mechanics, we'll just call it kind of quantum technology as a placeholder, how much of what you teach and what you learn is theory, and how much is generally accepted? Is there a percentage of, are we 99% theory and working to get 1% of the time accepted? Or tell me how all that is, if that question even makes sense to you.
Yeah, it makes a lot of sense. And I think it's a good place to kind of start a conversation about it. So you mentioned quantum mechanics and mentioned the 30s. So around the end of the 1800s, around 1900 or so, people realized that, well, there was some claims that physics was done. Everyone solved all the physics problems. It's just, except a few small, mysteries, whatever. And then this whole mysteries opened up into quantum mechanics writ large. You have this idea of chemistry going back to thinking about molecules and atoms. Ludwig von Boltzmann was founder of statistical mechanics, and he realized that there had to be quantized particles. People who do music often see quantum quantization. So you have you have different harmonics of an instrument, and these are all quantized based on the size of the instrument and the shape of the instrument. And so a lot of these things end up being quantized naturally. And so there's nothing theoretical about it in that sense. I think what has become new in the last 10, 20, 30 years even is the engineering side of quantum mechanics. It's really being able to take the fact that we understand how atoms and molecules and how these things connect to experiment, how these connect to theory, and how the theory connects back to experiment, all these things. Now, can we take those understandings and engineer something? Can we make something out of this? Can we then use these effects to do something interesting? So I think a lot of science starts off with quantifying something, understanding that something's wrong, realizing there's some problem here, and then quantifying what's going on, checking your theory against what you predict it to be, improving your theory, and then coming with an experiment, new theory, new experiment, new theory, new experiment. So quantum mechanics is a very important interplay between, what the theory says and what the experiment says, and that's actually how we validate the quantum mechanics is a theory that holds a lot of validity. The Nobel Prize last year was around violating inequality that Einstein had put forth, or not Einstein had put forth inequality, but Einstein put forth the idea that quantum mechanics was not correct. And so proving that it is correct has been a small cottage industry for many years that resulted in a Nobel Prize last year.
So Einstein, which is generally, at least from my perspective, held in high regard scientifically, he was wrong about quantum mechanics.
Yeah, profoundly wrong about quantum mechanics. And it's really interesting because he did some very seminal works that really laid the foundation for the mathematics and the understanding of the quantum mechanics, and even won his Nobel Prize for quantum. But I think the Bohr-Einstein debates, he was on the losing side of that argument. That's just all the arguments that he had with Bohr and Einstein. I mean, he said God doesn't play dice. I mean, probability is at the heart of quantum mechanics, and in the way that I think about it, and the way that I, try to explain quantum mechanics. So let's start with probability first. And Einstein famously said God does not play dice, and this, I'm not sure if it's actually his quote, but it's often attributed to him. And this is not the right way to think about quantum mechanics. And he had this EPR paradox, and again, was not the right way to think about quantum mechanics. So a lot of things that Einstein, I think, conceptually overlooked. I think his skill and ability as a physicist did not match his imagination as a philosopher. Not to knock anyone too hard that's
Sure.
around argue against.
Interesting. Yeah, interesting. I'm going to ask you a very short question, which will no doubt solicit a very long answer. And it's almost an unfair question, but you're in the educational business, so I'm just going to throw it at you anyway.
Yeah.
And answer the question as if your audience all has a beginner's mindset, for my benefit, and probably for some of my audience. What is quantum physics / mechanics? Is there is one a variation of the other? But let's just kind of back up a little bit and tell me about the whole quantum technology in a kind of a layman's term. And this is something Baird says you'll have to be labeled a miracle worker in order to do it. So we're gonna kind of test that theory as well.
Yeah, I mean, I think it's not so hard to explain, depending on the level that you're interested in. Very much so, thinking about a car. If you think about a car, there's a lot of details in there that you don't care about if you want to know what the top speed is. Top speed, you don't care about the the injection cam cycles. I know this stuff is important. You just want to know how fast does a car go. And if you don't care about the details, it's one thing. If you do care about the details, maybe you don't care how fast the car goes. You want to make sure it's engineered correctly and that the fuel efficiency is high or whatever. And so quantum mechanics is the same thing. You can zoom out and really care a lot about the details, really get into how this applies to atoms, molecules, solids, nuclear physics, and how this might understand the world around you. Or you could think, well, how does this affect my bottom line? How does this affect my engineering? How does this affect what I want to build? And I think more than quantum physics and quantum mechanics, I think the major difference that is really coming out now is quantum technology versus quantum mechanics, quantum physics. And I really like, I heard this quote once, someone said that their goal was to try to get people from quantum mechanics to quantum engineers. And so I think this is really where a lot of the transitions going on in the industry, where it's a lot more companies involved and a lot less academic, well, not less academics, but academics is still important, But now there's a lot of companies being involved, investing large amounts of money, not just U.S. government, that are really trying to engineer these devices and create things. So that's the difference between quantum technology, where you're trying to build something, and quantum engineering, or quantum physics, quantum mechanics, where you're thinking about how does this stuff work and all. And I think a little bit about quantum mechanics, and the way that I think about quantum mechanics, the way that I like to teach quantum mechanics, and I think all my students will at least already have heard this 1,000 times, but probability first. So if you think about how probability works, it's usually pretty easy to explain to someone who's an engineer, physicist, anybody in the quantitative field, what probability is. You just ask them, 50-50 probability, they get an intuitive sense of one half showing up somewhere, and they can say, 2/3, and they know fractions, okay, everything's fine. And if you take the principles behind probability and really understand these, that's a very good way to start thinking about how quantum mechanics affects that. And so the way that I think about teaching quantum mechanics, and in fact, I'm trying to write up my notes now, is if you think about how probability functions need to transform, then there's a lot of structure around it to make sure that it stays normalized, make sure that it stays positive, make sure nothing becomes negative. And so you have these couple properties you want to hold on to. And if you start quantum mechanics in the same way, you can start off with something that generalizes the probability function, and you have a probability matrix. And this matrix now has a bunch of properties, and you need the eigenvalues to be to remain real and sum up to one. And the eigenvalue doesn't make any sense. Okay, we zoomed a little too far, but nonetheless, the idea is that there's another object that's like the probability function that you just need to preserve all the properties, and that gives you back the structure of quantum mechanics quite nicely. And then you could think about all the problems that show up in the engineering side, which is sampling, which is around making sure that you maintain what state you want it to be, and it stays that state for as long as possible, that you don't have any, unwanted noise sources, changing how the system evolves, changing, the measurement, changing, what's going on inside the system, that if you have probability distribution of red and blue balls and you reach in there and grab out a blue ball, if you did this, it's fine, you get measuring probability distribution. But if a rabbit starts grabbing red balls and a bee flies by and it, takes away a blue ball, and you don't know, there's different things in the environment.
All these variables, yeah.
Yeah, and that's really what happens in quantum when you start trying to engineer quantum mechanics. You start having a lot of things from the environment affect the system that you're trying to control. And so we talk about quantum computing, quantum technologies. It's really about controlling quantum systems, controlling quantum devices, controlling the evolution and behavior of these quantum objects. And this is hard to do because there's other things that are interfering with this. If you have an easy access to control this system, well, someone else can hijack it. Not even someone else, but something else. That if you have a laser coming in, you can imagine a light from the room might affect it. The temperature inside of the room might actually be one of the major causes of problems. And so a lot of the quantum devices are at cryogenic temperatures. And so this is a whole aspect of it to reduce noise and isolate it. At the same time, you have some systems that need to be very high vacuum because the gas particles might hit it. And if a gas particle hits it, it also causes the system to heat up and lose information. And so this whole idea of protecting information is really where you have quantum mechanics intersecting with information theory. You have this quantum information science and quantum technologies coming out of that, thinking about sensors and things like this. They're all applications of the fact that we understand how quanta work.
Interesting. We seem to have history repeated, at least in one sense. I remember, I believe it was in the 70s, the Cray supercomputer, which, by the way, is basically this now, right? It's basically the cell phone. But the Cray supercomputer was immersed in a cold liquid called fluorine, which was a non-conductive, dielectric liquid, and they did that to keep it cool. I don't think it was sub like cryogenic, like you're talking about. But those computers generated some heat and they needed to stay cool, so they dipped them in fluorine. And quantum, I know IBM's so-called quantum computer, I'll say so-called because I have a question on it, is also, it is cryogenically operated, right? From what I understand, but for different reasons. Not because, I think in the Cray sense, it wasn't that the heat would make 2 + 2 5. I think in that case, the heat would cause something to melt and catch fire, or burn up. In other words, that kind of brings me to this question. I always kind of crack up over the latest in science being hijacked by some corporation's marketing department, right? And I see that right now in artificial intelligence. The term AI seems to have made its way into Madison Avenue, and I'm hearing all these commercial products, consumer products, toothbrushes with AI and et cetera, et cetera. Now, maybe there's a sliver of truth to that, if any. But have you seen the term quantum, whatever, quantum mechanics, quantum physics, quantum technology? Have you seen evidence of that being commercialized in maybe computing is a good example, because I've certainly heard of quantum computers, and I'm thinking of IBM now, which may truly use quantum technology. I don't know, and I've read articles that these like ChatGPT is so powerful it has to be run on quantum computers, and I'm not sure if that's actually accurate either. But what's your take on how much of the regular everyday Joe conversation about quantum is actually what you understand quantum to be? Does that make sense?
Yes, it does. It makes a lot of sense. There's a lot to say here. I don't want to.
Good.
But hopefully I don't step on any toes here. But yeah, this is perennially a problem, I guess, for every new technologies that the PR is not the engineering department. They just write whatever they want to write. And this has been a problem with quantum computing for a long time. I think going back to some of the early announcements by D-Wave many years ago, where they had really oversold what they had created. I think now a lot of the larger businesses are very conservative about what they're saying. So at AWS, we try to, be the voice of reason as much as possible. But I think a lot of companies, they need to make their shareholders happy. You have to make your Series A, Series B, whatever. You need to get, drum up funding. And so you need the hype to actually maintain the investment. And I think there's a certain aspect of it that's not entirely hype. I think a lot of companies, a lot of news cycles end up hyping things that don't need to be hyped. I think a small experiment to play around with the toy system gets said, well, quantum computers will do blah, blah, blah thing that's, way oversold. In my own personal opinion, I work on some things that I think will work, but I think a lot of the scientific literature has misleading content, and not necessarily misleading because people are trying to be misleading. Sometimes they just don't know, they just, they're new to the field or whatever, and they're going down this route because they can make some progress, or, this is at least something that works today. And so there's a lot of things that end up being today's hype, and there's a lot of questions of what's going to survive till tomorrow. And I think, thinking what the business model will be, how this will actually affect companies, how this will actually play a role in society. Right now, the devices are small, they're noisy. This is a podcast about reliability. So if they're not very reliable, then that's exactly what the whole issue is. And so without the devices being at scale, there's really nothing that needs to be said to consumer level. I think also, even as a consumer of quantum technology, and whether it happens to be a ChatGPT or not, it will be cloud computing. Most likely, almost all the companies that are doing quantum computing have enabled cloud computing access, cloud access to the devices. So people aren't selling the devices as much as they're selling access to the device.
Right.
And so what you can expect will happen more likely than it being something that shows up at your front door. Rather, it'll be something in the cloud. You ask a question to Alexa or Siri or whatever, and then maybe it runs some quantum computing job or ChatGPT. If someone really figures out a way to use quantum computing to speed that up, it wouldn't show up on the consumer side either. It would just, you ask Bard, and Bard tells you something, and use a quantum device, then use a quantum device. And so I think a lot of this will be very much behind the scenes when it does come to fruition. I think a lot of the hype cycles are, people have to make their investment somewhere or another.
Right. And some of it may be to drive funding and things like that, right? The larger, the grander the promises, the grander the someone wants to fund it, right? Because it will land on their P&L at some point. I think that's just human nature. But it does crack me up when I'm aware of a certain technology, not so much quantum, and then I see that bounced around in kind of layman circles, in consumer circles. It's just funny to hear the interpretation. It's like that old game of telephone. You get 10 people in a row and you whisper something into each one's ear, and what comes out the other end gets something completely different. I'm using the term quantum physics and quantum mechanics almost interchangeably, which is probably not totally accurate. But what is the difference between quantum physics and quantum mechanics? Is one just a deeper dive into the other, but help me understand that.
Yeah, I mean, there's nothing really. I mean, there's
Okay.
just words. And maybe to zoom out a little bit, they're just words, yes, but people use the words to mean certain things. So there's quantum chemistry, there's quantum physics, there's chemical physics, there's physical chemistry. There's, it's a bunch of words soup. You kind of put them in there, and then you feel like you want to say quantum mechanics one day. And if you're in the physics department, you say quantum physics. If you're in the chemistry department, you say quantum chemistry. And then if you're, just teaching a class where you call it quantum mechanics, and if you want to call it quantum physics or geophysics, it's just words, really, at some high level.
So the operative word is quantum. Quantum is the defining term, and then the next one is just the context that you're defining it in. Is that fair?
That's much fairer than thinking there's something deep differences. I would say that in quantum physics, a lot of times you're thinking about very much physical protocols. You're thinking about how the physics intersects. So in a quantum physics textbook, you might start off with the atom and how the quantum mechanics of the atom, dictates a lot of understanding of materials and matters, and maybe go into the quantum mechanics of nuclei, or maybe go into the quantum mechanics of fundamental particles. You can start zooming in. And if you think about quantum chemistry, well, you zoom out. You start off with the atom, and you go to, multiple atoms. You start talking about molecules and bonding. And then you start talking about how this affects molecular dynamics. And so you're zooming in and zooming out in different directions. And they just, it's such a bifurcated field that you need different names to kind of say where you're at. So if you say a quantum physics textbook, you expect to talk about physical experiments, talk about the Nobel Prizes in physics, more so than Nobel Prizes in chemistry, which are often driven by quantum mechanics. And so it's not that quantum mechanics ends up being different. It's still, you have to still have the same notion of quanta. You still need the same mathematical framework. You still need the same setup, more or less, and then you just have different applications of that. And you can't fit everything in one textbook, so that's why they have different names for different books. But quantum is the operative part of it, that it's quantized at some level.
So I did some research on, to prepare for this conversation, and as much as I could. And one of the definitions of quantum mechanics was, and among other things, understanding the properties of semiconductors. So okay, that's one application of quantum. And then I started thinking, and kind of this paradox appeared in my head. Semiconductors don't grow on trees; they're man-made. Semiconductors were made by us, right? And now, all these years later, we have a whole field of science that studies what we have already made, right? So okay, I'm not quite clear on that, but let's just go with that. The first semiconductor in its primitive form was a rectifier, an AC-DC converter, back in 1874. Technically, that was a semiconductor, or at least a very primitive version of a semiconductor. Decades later, Bell Laboratories invented the point-to-point transistor, 1947. Arguably, it's got its roots in semiconductor technology. And Shockley invented the junction transistor in 1948. So semiconductor technology in some form or another, even primitive, have been around for over 100 years. And now we have a science that is studying the technology that has been around in one form or another for more than 100 years. Is that an accurate interpretation? And if so, is it common for us humans to invent something and then spend centuries potentially studying what we've invented to understand how it works? It seems to me if I invent a wheel that turns, I kind of know how it works because I invented it, right? But I'm super oversimplifying that question, but just to make a point. So comment
Maybe
on that if you would.
Yeah, I can comment on that. I think I can comment pretty extensively on that. So I guess If I understood your kind of your question here, you're saying semiconductors have been around for over 100 years, but really semiconductors have been around since, sand, right? Silicon, all these sorts of things.
True.
Well, the things that don't conduct super well are semiconductors, right? If it's a
Yeah.
conductor, and
Yeah.
it doesn't conduct at all, semiconductor somewhere in between. And the whole idea of semiconductor technology is that we can control how much it does and does not conduct. And this is doping and all these different types of junctions, and you have the N and the P junction, and you have different types of gallium arsenic, and you have these different ways of combining semiconductors to make technology out of it. So it's not just that we have semiconductors. I mean, we had semiconductors just because some things conduct well, some things don't, and there's something in between, and that's what semiconductors are. But making that into technology and really having that as an industry, being able to manufacture, fabricate, cut, design, and combine different types of semiconductors, really where the technology comes in. And I think if you think about something like inventing a wheel, right, there's all sorts of technology around wheels. What kind of rubber we use, what kind of wheelbase it is, whether you use alloy, different alloys for the wheel spokes. And I don't know, it's engineering podcast. You guys must know much more about how to engineer a wheel, but people still study engineering of wheels. That I don't think it's not surprising that people go deeper and deeper and deeper into it. I think one of the interesting things about quantum mechanics is I teach a course called solid state physics, where we go through the quantum mechanics of conducting semiconductors. Talk about an electron, what's quantized electricity. And you think about how the electron behaves, and you have its cousin, the hole, which is a missing electron, and you have these sort of things and how the dynamics are as individual particles and as collective particles, the behavior thereof. And that's where you get into quantum mechanics explaining what's going on physically. Even if you made a semiconductor, or you made some semiconductor rectifier, well, how does it work? What are the details behind this? What kind of semiconductor did you use? Did you use a semiconductor that's doped? Did you use a pure semiconductor? Not pure, intrinsic semiconductor or extrinsic semiconductor. So there's different types of ways of thinking about how do we actually engineer, control, devise, understand, or why did it 100 years ago, right? So you think about Newton wrote down the physical laws for how the planets move when he wrote down his equations, 1600s or so. Been studying them ever since, right? Still teach Newton's 3 laws of mechanics, right? And so it's not that you stop studying things just because you made them once.
Yeah, no, that makes a lot of sense. It's and you're right. There are plenty of examples of the study of existing technologies to expand its application or improve its use. I guess that's the reason computers are faster today, and that's the reason phones are smaller today, and that's all of that, right? It's evolution, I guess. Maybe revolution was the discovery of turning sand into semiconductors, and then evolution is what we're going through and all the various progressions of it. For the person in the electronic, most of my audience is in the electronic assembly space. We're assembling circuit boards and putting them in things and hoping they don't fail. In your world, in your experience and opinion, what can we expect to see in the future that will rock our world as a result of the study of quantum technologies?
I think it's a really interesting question there. What we'll see in the future, what you see now. So right now, there's already tons of quantum mechanics, almost everything. I remember going to your talk at the conference in Hawaii, and you talked about chemical reactions. Talking about diffusion concepts, and these are all quantum mechanical concepts, right? These things have underlying quantum mechanics as to why they're true. Why did this reaction proceed? Well, there's some electronic structure, there's some nuclear behavior, there's some interaction with the electron and wave functions, and then these things find it more energetically favorable to be in one form or the other. And whether it's polar or non-polar, you look at the wave function and whether the distribution of charges are asymmetric or not. And so this ends up being the underlying reason why these things are true. But if you don't care about the underlying reason, it's like driving a car. Again, you just drive the car. You don't really worry about the details of it. And I think for the long-term, distant future, in the same way that components of a transistor are very much, isolated from the person who's making the making making the board. They don't need to go in and do the wiring on every single part. They have them in IC component and put them in and solder it on or whatever. And the same thing I think will eventually be true if quantum mechanics gets integrated far enough that then you have some piece of a chip that you just fabricate on the board, and that might be 100 years from now. I don't know if it's that long, but to really have it miniaturized to the point where it's integrated circuits that you're putting onto a board, that we're very, very far away from that as far as quantum technology goes. But I think that at some point it has to become an engineering problem. When it's an engineering problem, you want everything to be encapsulated into different silos of problems that you solve. Solve the resistor problem and put it this little integrated circuit component, and then you could put into your whatever you want to put it into. And so when we start building up quantum devices the same way, I think that'll be part of what it has to become, just for it to become a engineering solution. I think that's where the distant future is, and I think right now we're still trying to get anything to work. And I think in many ways the quantum mechanics is already there. If you're dealing with chemical reactions or dealing with electricity and magnetism, I mean all these things all require quantum mechanics in many ways. And it maybe don't need to use quantum mechanics at all times, but that doesn't mean it's not there.
Yeah, it's there in the background, whether we recognize it or not. Like sand, we've always had semiconductor materials. We just didn't know how to put them together. I've read that some of the challenges of using quantum mechanics in the electronics industry include the difficulty of controlling quantum systems, the need for new materials and devices, the need for new manufacturing methods. Do you agree with those challenges? And if so, how are we going to overcome that?
I think circling back to something you said earlier about the devices that are cryogenically cooled, and the difference between cryogenically cooling or not cryogenic, but cooling a CPU that's heating up as a result of doing processing. For the quantum computing and a lot of the technologies that are being pursued around superconductivity. Superconductivity requires very cold temperature for the resistance to basically drop to effectively zero, and then you have a lot of other properties that come in. And those properties that come in and you can exploit for quantum mechanical computing purposes. And what I think a lot of people working on as far as material science goes is getting high temperature superconductors. So if you got high room temperature superconductivity, well then great, we can make room temperature quantum objects that we can then control or otherwise manipulate. And hopefully then that gives you something to put in your pocket, right? Integrates directly into semiconductor technology. And so some places and some companies are pursuing things that are quantum mechanical, but already integrated in semiconductor technology such that it can be scaled up almost immediately. But the whole name of the game is really around that.
Interesting. How do you think quantum technologies will land in products that everyday people, maybe outside of our world, outside of your world and my world, engineering, education, will see it? What do you what's I remember in the 60s I used to love Popular Mechanics and Popular Science magazines. I couldn't afford to buy them, but I would go to the drugstore and look through the magazines and read all the articles I could. And they promised us flying cars by the year 2000. Year 2000 was the benchmark of when all these futuristic things were going to come to fruition. And they promised us flying cars, among other things, and robots in the house, and we do have some of that. But what's your kind of nirvana in terms of the application of all of this study and all of this science? Where do you think it's going to land on civilization, and how do you think it will benefit society and us humans?
So zooming out, I guess, to the beginning of our conversation around quantum technology. So what is quantum technology? I mean, this is really where you can get into marketing from the beginning, right?
There we go.
Versus quantum technology versus quantum physics versus quantum chemistry. They're all just words, right? There's no real, there's no meat behind the words. I mean, there's meat behind the words, the way that the user's using it, but there's not an established definition of what these things are. And so we say quantum technology, in many ways, you can't build a semiconductor device at nanoscale, fabrication without using quantum mechanics. So technically it's quantum technology, and depending on how you define these things. I think one of the most interesting ways that quantum mechanics intersects people's day-to-day lives is in atomic clocks. This is really beautiful physics, and it's really beautiful quantum mechanics, and it's really interesting to think about how time works. These guys measure time so precisely that the concept of now does not even make sense neurologically, because the speed at which neurons fire, you're thinking about timescales that are far below the speed at which potassium ions go out of a channel, right? So there's no concept of thought at that speed that they are able to record and track time. It's really amazing.
By the time you think of now, it's already history, right? I mean, it's simultaneous. Now is almost simultaneously history.
It's crazy. I mean, yeah. I mean, I'm still like flabbergasted by the concept of relativity. I mean, I know I'm a physicist and all, but like, still very hard to wrap my mind around like things happening at the same time. Just shift point of view, and now they're happening at different. It's really amazing.
Yeah.
But they're measuring time at that scale. These questions become relevant. So the time dilation, I was reading an article the other day, and they're talking about keeping track of time on the moon. They keep track of time so well that time is actually different on the moon than on the Earth because of difference in gravitational potential. And so,
right, gravity and time are interrelated. Yeah, that's an Einstein thing, right?
Exactly, it is indeed. And so when you have quantum mechanics giving you sensing capabilities, understanding what's going on well enough to engineer something better, to fabricate at a smaller scale, then in some sense it's all quantum technology. Like I said, I mean, if you're using the principles behind it, you're using chemistry, well, it's quantum chemistry because it's quantum, it's electrons involved and atoms and molecules. That, where you draw the line between what's quantum technology and what's just technology, it's not entirely arbitrary. When people talk about quantum technology, they're talking about not just using quantum mechanics as a means to an end to generate something you already had at the larger scale and just try to scale it down, but really thinking about how do I use quantum mechanics, coherence of quantum systems as a resource. Eventually we get to quantum computing, quantum technology. But when will they see it? I mean, in your cell phone, right? You imagine having a sensor that relies on some quantum mechanical property. I mean, arguably, you might already have quantum technology in your pocket. Whether or not you call that quantum technology, if that's just sensing, it's up to you.
Interesting. I have some university students who claim to listen to this show, and if there's a person entering university and they have an interest in quantum theories, quantum technology, what would be your best advice for them in terms of maybe undergrad or prep? What do you tell emerging students that express an interest in what you teach?
I don't know what level of university your students are, but I would say for quantum computing, and when I give as advice to most people about graduate school, more so than undergrad. Undergrads, I mean, do whatever. It doesn't really matter. I mean, it matters, but you can apply for a job with almost any degree. As long as you have, some calculus and, differential equations. What's the difference? You're an English major, means you can write well. If you know the math and science, you get to work, right? And it's not much of a big difference. I think my advice would be, get your technical skills together. This is one of the major problems that you have as an undergrad anyways, is that if you didn't take the time to learn calculus 1, 2, and 3, you're going to be out of a lot of conversations that we can't have any further. And that's because calculus 1, 2, and 3 in differential equations is true, whether in biology, chemistry, physics, whatever. You have to take the calculus sequence, and you're scientists. I mean, not because of that, but now you're able to go and decide later, I want to know more about this, I want to know more about that. But if you don't have the foundation behind it, it's very hard for someone to start teaching it. I think for more of the advanced degree students in quantum technology, so if people come to my research group and they say, I want to do a PhD in quantum technology because I want a job. So that's the wrong reason to do a PhD altogether. Like, you shouldn't do PhDs for job purposes. Go get a master's degree, do some online certificates if you want a job. But if you want to learn something deeply, pick something you're really engaged with, really enjoy, and go enjoy it. That's what the whole entire PhD game is, that you get, 4 or 5 years to close out everything else. You don't have to worry about funding, don't have to worry about, the newspaper or whatever. Just sit here, and here's as many books as you can get through in the next 5 years. Come back and tell me something interesting. And that's your job as a graduate student. And I think that's really about picking something you're passionate about. For me, I got into quantum computing, quantum mechanics, because someone gave me a book, Nielsen Chuang's book, and I started reading it. And I just, kept going. And there wasn't really anything else. I really enjoyed it. I liked linear algebra. I liked, the aspect of quantum mechanics that I had learned from chemistry, and then just kind of bringing that more and more to center stage inside my mind and studying deeper and deeper was how I got into it. And not because there was a bunch of companies involved or anything of that nature. So I think the companies came many, many years after I'd started studying quantum mechanics. That, maybe D-Wave was around at the beginning, but other than that, there was not a huge industry. There was no large corporations that were involved in studying quantum computing when I started. And you got to do something you love. I think that's really the right way to think about how to go and to study something. And if you do something you love, well, you can be employed in many ways. And I think whether it's in quantum industry or whatever comes after, or AI or whatever, you need the skills and training to be there. Knowing statistics well will put you in a good position to contribute to ML or contribute to psychology or to whatever else you want to do. So I think as an undergrad, get your background together.
Yeah, good advice.
One piece of advice for all undergraduates. One course I think everyone should take is computer science. Just basic programming. I think that, it's past the point and it's so simplified that everyone should know a little bit of programming. Like everyone knows how to write in English.
Yeah. I'm a huge believer in that, and I would actually bring that into elementary school. I think learning to code. I learned to code when I was in high school, and it was basic back then. But I used to write games that could be played on a teletype machine. We didn't have monitors back then. We phoned in to the mainframe computer at the school district, and we had a handheld phone, and then we stuck the phone into this suction cup device, and that was the modem, and we had a teletype. Our user interface was a teletype machine, and it was so it was just rows of typed text. But I learned to write code, and then advance 15 years or more after that, I started a company, which I still own today, 31 years later, and the early days, we are an equipment manufacturer, and the early machines used to run on software. We had controllers, programmable controllers, and the language of choice for those controllers was a dialect of BASIC. And I remember, I know BASIC. I remember that from high school, right? And I wrote all the code for our machines the first few years. But I do think that if we teach young people, and I say young, I'm talking about elementary school, preteens, if we teach them simple coding, I think that teaches someone how to think analytically. It teaches them how to problem solve, because life is full of if-then statements. If, then, else, right? If this is the case, we do this or that, else this. I think it really, to me, it helped me think analytically. It helped me problem solve. And when I was deep in my coding world, when we were doing our big, massive coding events, and I would go to the office for 3 days straight and not go home and just sit and code, I remember thinking, I would go to the grocery store to pick up some Diet Coke or something, and I remember, it's hard to describe, but I would think of what I'm doing as if I was writing code. Go down this aisle. If it's not here, else go to that aisle. And I had to stop myself. I had to slap my face and go, okay, I'm not writing code right now. I don't need to think in terms of code blocks, right? But I did. And I don't know. I just think your advice is amazing for, university level students. But I think that even sooner, get kids exposed. I think learning how to code, or at least the concept of coding, is just as important as mathematics and science
So I would put coding in the English side of things much more than in the math and science side of things. I think your story, I think, is really cool, because when I think of computers, I think back to Turing, Alan Turing. He wrote about the Turing machines, and he was not thinking about digital devices. He was thinking about a person who had a pencil and paper and how it would give instructions to follow to some procedure. How do you add large numbers? Well, here's a procedure you follow. And you can imagine this is exactly how teachers could teach students. I mean, it's not a very fun way to teach, first carry the wood, okay,
right,
add column here and erase it. And you could walk someone through the procedures for adding large numbers as a Turing program. And that would be for someone to know. I think it's a terrible way to teach, but, the concept is that you're absolutely right. As a person, you need to make some procedure for how you're going to solve a problem. I need to do this first, second, third. What's the most efficient way to get there? And so I think it makes a lot of sense. I mean, I like this coding language, Scratch. My daughter uses Scratch. And this is a really cool programming language. All the if statements, then statements are all like little blocks. They fit into the box, so you can't do the syntax wrong because of the shapes.
Yeah.
It's very nice.
It's a graphical language as opposed to just strings of text, right?
So the text is in graphical format. So if they has like a little bracket with an if at the top and a then at the bottom, and a little space to put code that fits in between those little sections.
Yeah.
So it's all like, very intuitive, and I like it because it's a nice way to kind of get started. I mean, I learned BASIC as a kid too. And I think with BASIC, the fun, like, full story about it is that it was made at Dartmouth. So this is one of the fun facts about BASIC. So, I learned it. My dad really loved computers when I was a kid, and he all sorts of computing devices. And I didn't realize until I was an adult that he got us all in video game systems so he could see how the technology was progressing too. But I mean, I made a chicken walk. My big accomplishment for the summer. It's like a little yellow blob, another yellow blob, and an orange triangle for a beak. It's orange leg.
Early animator.
Yeah, exactly. I was like, cool, I got a graphics. Let me make an animation.
Oh, that's cool. Very good. And last question. We're about out of time, but time flies when we're talking quantum. The two things affect time: gravity and recording a podcast. I think there's a theory in there somewhere that someone will discover. And coding time. When you're coding, time stands still, right? My wife would say, no rush, but when do you think you'll be done? Oh, 20 minutes. And then like an hour and 45 minutes later, she'd come and go, are you done? I said 20 minutes. She goes, well, that was an hour and a half ago. You just lose track of time.
Mine is 3.14 times whatever my estimate is.
Right. Exactly. My wife calls it software time or and frequently mic time. If quantum X, fill in the blank, quantum technology, the study of quantum, whatever, were an iceberg, how much of that iceberg is above the water and how much is still yet to discover?
That's a great question. I guess for a very high level philosophical, go have fun on Wikipedia after you finish this podcast, point of view on it, is there's this whole matter in physics, very much like I mentioned, around the turn of the century, 1800s, in the 1800s, started 1900s, people thought almost everything's done. It's very clear what the principles are, but there's some small mysteries that people haven't solved. And I think now we're at the same place in science with different mysteries. This whole concept of dark matter is really amazing and really interesting. And I think, there's a lot of questions from an astronomical point of view of what that is. But in the same way that a lot of astronomical questions were addressed, in fact, we talked about Einstein several times, but relativity is how we solved Mercury's orbit. It's very hard to compute, but you need to take into account relativity to do it correctly. And Einstein figured this out, but this is a terrestrial problem, terrestrial theory about the speed of light, very constant, and you extrapolate and it starts to tell you something about space. And I think that'll be really where quantum mechanics is still missing. There's a huge problem with how quantum mechanics treats time. Maybe not huge, but there's a problem with how quantum mechanics treats time. And this means that there's some real questions about how general relativity and quantum mechanics mesh back together. And this, I think, if you do it right, should also address this dark matter problem. I don't know. I mean, I'm not a dark matter researcher, but this is where I think there's a lot of opportunity in all forms of science that if anyone figures something out, and they figure the whole thing out, there's got to be like a missing puzzle piece. We put it in, and it'll all click. Like the theory of relativity is really nice because it's not super complicated. I mean, yes, it is complicated, but the core of the idea is like a missing puzzle piece. And you have to extrapolate the puzzle piece out, put it everywhere it goes, but you got to get that puzzle piece first. Like understanding quantum mechanics in the first place. Okay, cool. I understand quantum mechanics looks like this. Well, how do I understand atoms, molecules, semiconductor technology, fabrication, everything? Right? How do I understand, reactions, all these things from quantum mechanics? And I think we're going to have to find something that's a missing puzzle piece about dark matter, dark energy. And I have no idea what it'll be, but I think the study of quantum mechanics at some point will hit pay dirt, or, studying relativity also hits pay dirt or whatever. The studying these things at some point has to come back together to make the whole thing make sense.
Yeah.
So
excellent. So we're seeing quite literally or metaphorically anyway, the tip of the iceberg right now.
yeah, there's always more science. There's always more science. I think that's the fun part about science. Is you can't be done. I don't care ChatGPT or not. Like, we're still going to have scientists needed. There'll always be questions and mysteries that we want to know more about.
Sure. And even if ChatGPT or something like that is what, the future has been promised it to be, it then will reveal things that will require more study and things like that,
Yep.
right? It will reveal the whatever then version of sand. It's always been here, and we're just discovering, like, oh my God, this could be used for X or Y or whatever. And then someone will come up with a theory on that, which will be proved or disproved and argued about for the next century. And it's wash, rinse, repeat, right? It's just, It'll just happen. Yeah. Excellent. Well, Dr. James Whitfield, Professor Dartmouth, among many other things that you do, thank you so much for your generosity, for sitting down for the last hour, a little over an hour, with me and my audience, and talking about this fascinating subject. I'm envious of what you get to do, because you get to teach students, which they're my favorite group of people to speak to, and it's just such a fascinating, fluid subject. You're teaching in real time as the evolution is being discovered, and so what you teach today could be quite different than what you teach next year, because more is being discovered. So you are actually in a kind of a unique and enviable position of learning and teaching kind of simultaneously, because it's not like you're teaching plain old mathematics where the rules just kind of tend not to change, right? Methods may change, but the rules are basically the same. You're teaching something that we're still discovering. So that's to me, that's quite remarkable. So thank you for sharing all that information with me and my audience. I really appreciate it.
Thank you for on the show. I'm really, really happy to take the invitation. I'm really happy to be here. Thank you again for having me on.
Oh, my pleasure. Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Our episodes have been downloaded more than 35,000 times. That just amazes me. And I remain ever grateful for your support and encouragement. Don't miss an episode. You can subscribe to Reliability Matters on pretty much any of your favorite podcast apps, or if you'd prefer to watch the podcast, then you can view it on the Reliability Matters YouTube channel. And while you're there, be sure and click the subscribe button and the bell icon to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday of each month. And a special thank you to our friends and colleagues at Circuit Assembly Magazine's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Thanks also for your questions and episode suggestions. Please keep them coming. You can send questions and episode suggestions to my email address, which is mike@mikeconrad.com. Just remember, that's Conrad with a K. Once again, thanks for listening or watching. Until I see you again, stay safe, stay healthy, stay happy, and perhaps most importantly, keep doing it right. And I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.